Hello, everyone. My name is Sipong Sanrao. I'm a research scholar from the National Biotechnology. Today, the topic of my presentation is biomass-derived heterogeneous catalysts for synthesis of solketal and biodiesel byproduct Glycerol. These are the outlines of my presentation. Before I start, let me draw your attention towards fossil fuels and its depletion. 80% of energy consumption comes from fossil fuels, and due to this over-excessive use of fossil fuels, there cause some serious effects such as increase in greenhouse gases, which will lead to global warming, decline in health, and over-excessive of fossil fuels leads to depletion of natural resources, which will lead to industrial sector and shutdown and loss in economy. And it has been reported by International Energy Agency that by the year 2050, fossil fuel will be exhausted. So we have at the most 30 years to find an alternative. Keeping that in mind, biodiesel, also known as biofuel, stands out to be a promising fuel in this factor due to its various advantages such as its renewability, abundant availability of natural resources, its non-toxicity upon combustion, and sustainability. So what is biodiesel? Biodiesel is also known as fatty acid methyl ester. It is obtained by the transesterification of vegetable oil or animal fats in the vicinity of a catalyst. It was first synthesized by Rudolf Diesel in the year 1890, where he used the feedstock of peanut oil and synthesized the biodiesel. Scheme 1 shows the mechanism reaction where 1 mole of triglyceride reacts with methanol in the presence of a catalyst to form a biodiesel and a glycerol byproduct of 10 weight%. And in order to sustain the industry of biodiesel, with the major hindrance to this field is that of its cost effectiveness. So in order to sustain this industry, we need to valorize this byproduct glycerol into certain value additives because it has been reported that annually 2.2 billion gallons of glycerol is being generated and wasted. So keeping that in mind, glycerol was subjected to valorize, and the major product that was formed was solketal. So what is solketal? Solketal is a 5-membered ring product obtained by the acetylation of glycerol and acetone, started way back in the year 1895. And ever since then, solketal was synthesized. It finds application in various types of pharmaceutical industries, fuel additives, and polymer industries. Over the years, different types of heterogeneous and homogeneous catalysts has been explored. However, due to various types of limitations, there's still search to find a better catalyst for this process. Biomass-derived catalyst, metal oxide catalyst, polymer catalyst, and metal organic framework has been explored. However, this catalyst, due to a certain limitation, biomass stands out to be a promising one, and biomass-derived catalysts produce no negative environmental impact, and the major positive of this catalyst is that the feedstocks are abundantly available. These are the various types of application from our laboratory work for the synthesis of solketal. Scheme 2 here represents the acetylation process where glycerol reacts with acetone and forming a 5-membered ring solketal, and a minor product 6-membered ring called dioxane is also formed with the liberation of water. So the target of our reaction was that to synthesize a highly active and efficient heterogeneous catalyst so that it would overcome the limitation of already reported catalysts. So keeping that in mind, we have synthesized a sulfonic acid functionalized aromatic carbonaceous material where glucose was used as a precursor, which was sulfonated using sulfuric acid in the ratio of 1:10 weight by volume at 80 degrees Celsius for 18 hours. And the product was further neutralized with distilled water and used it for the acetylation process. Under the optimized reaction condition, 1:5 glycerol to acetylene molar ratio, 6% catalyst, 10 minutes of reaction time, and 70 degrees Celsius. temperature under the microwave irradiation, forming a 5-member ring product called solketal. The novelty of our research work was that this glucose-derived catalyst was first ever used for the synthesis of solketal, and microwave irradiation technique reduces the overall reaction time to just 10 minutes. This is the proposed reaction mechanism for the acetylation reaction using our catalyst. Here, in the first step, the oxygen from the acetone abstracts a proton from the acidic group of our catalyst. Subsequently, the lone pair of oxygen from the glycerol attacks the electrophilic carbon, forming an intermediate state. And further, here two cases can be formed where if we follow the pathway of 2, then a 5-member ring solketal will be formed. And if pathway 3 is followed, then a 6-member ring called dioxane will be formed. However, in our case, we 5-member ring product was formed, which is known as solketal, and this can be further confirmed by the various type of characterization we have analyzed. In the coming slide, we will be discussing about that. So, in the resulting discussion, we have exhaustively characterized our newly synthesized catalyst. Firstly, scanning electron microscope analysis exhibit that our catalyst has a very loose and irregular network structure, as it can be seen. And the formation of particles at 550 to 200 microparticles was ascribed to the elimination of water during the carbonization process, and EDX spectrum records the presence of elements, carbon, oxygen, and sulfur, and it was detected that sulfur was confirmed, 4.28 weight % of sulfur was detected from this analysis. That means that successful carbonation or sulfonation of our catalyst was done. And the surface area and pore diameter of our catalyst was determined to be 3.56 meters square per gram, and pore diameter of 2.46 centimeter was obtained from the PET analysis. Data reveals that a hysteresis loop of type 4 isotherm was associated with our catalyst, confirming the mesoporous nature of our catalyst. Further, our catalyst was subjected to XRT, FTIR, and DGR analysis. And this FTIR analysis reveals that in the FTIR analysis, the broadband reveals that successful carbonization of the catalyst was done. And FTIR analysis here shows the presence of the acidic functional group and presence of active sites in our catalyst, where sulfonation was successfully confirmed by FTIR analysis also, where a peak at 1020 centimeter inverse confirms the presence of sulfonic acid groups. And further, the thermogravimetric analysis of a catalyst was studied, which shows that our catalyst was stable up to 200 degrees Celsius. Further decrease in mass was observed above 400 degrees Celsius, which was mainly due to oxidation of the catalyst from the carbonization process. So further, the successful sulfonation in the presence of elements was detected by extra photoelectron spectroscopy. Here, the peak at 283.6 and 287.0 electron volt were seen, confirming the presence of carboxyl group. Meanwhile, carbon single bond oxygen and carbon double bond oxygen peaks were detected at 531.3 and 539.4 electron volt. And the further confirmation of sulfonic group was detected here, confirming that a single distinct peak can be seen, confirming that one oxide sulfur was present in one oxidation state. And the overall XPS analysis give us the presence of sulfonic group in the catalyst, and 4.27 weight % of sulfonic group was detected, which was in line with our EDS analysis. Further, the kinetic study of our acetylation reaction was undergone. It is assumed that since acetone was taken in excess, the reaction will follow as pseudo first order kinetics. And this was the rate of the reaction was determined by using the equation 1 here. And activation energy of the catalyst was determined to be 35.8 kilojoule per mole, which was calculated using Arrhenius equation. And our synthesis catalyst was subjected to comparison with different other catalysts because the efficiency of the catalyst can only be determined by using calculating the turnover frequency. Here, it confirms that our catalyst has a higher turnover frequency than many of the other reported catalysts because of certain like using microwave irradiation, which reduces the overall reaction time to just 10 minutes in comparison to other methods, and a high conversion was formed comparison to other catalysts. Hence, it is proven that our catalyst is highly effective and efficient. Further, the product formation was confirmed by the analysis of 13 carbon, proton carbon NMR and GCMS analysis. Proton NMR confirms the formation of a 6-metal hydrogen of the product by forming a distinct peak at 1.30 and 1.24 ppm. Hydroxyl group was confirmed by the peak at 1.92 ppm. And the presence of CH and CH2 proton was confirmed by 3.7 and 4.10 ppm. 13 carbon helps us to confirm the presence of methyl carbon at 24.8 and 26.2 ppm. And CH and CH2 carbon was confirmed by the presence of peak at 76.9 and 66.5 along with 60.9, 62.9 ppm. Presence of kettle carbon was detected at 109.8 ppm. Further, the selectivity of our catalyst was confirmed by GCMS analysis, revealing that a full selectivity to solketal was obtained here in our reaction. And this is the beauty of our catalyst. And catalyst reusability is an important issue in terms of economic, industrial, and environmental point of view because it allows the reuse of catalysts while also lowering the overall cost and recyclability and of the manufacturing process. So the reusability of our current superchems catalyst was subjected to over 6 reaction cycles. Up to 5 reaction cycles, a high conversion was observed. However, on the 6th run, a slight drop in conversion was observed, which could be due to poor blocking and surface poisoning by acetone and glycerol. So we further try to confirm this deactivation by doing the analysis of 13 carbon solid-state NMR and proton solid-state NMR. Here, 13 carbonaceous NMR reveals a new formation of a new peak at around 50 to 80 ppm, showing that a remnant of glycerol is present in the catalyst matrix. And this was further confirmed by proton NMR, where we can see that a signal broadening or the emergence of shoulder at 3 ppm was formed. This further confirmed that the remnants of glycerol was catalyst present in the catalyst matrix. So it was confirmed that the deactivation of catalyst was due to the poor blocking of active sites by the presence of glycerol in the catalyst matrix. So in conclusion, what we have achieved in our research work was that we have successfully synthesized a sugar-derived heterogeneous catalyst for the production of solketal, and microwave irradiation method reduces the overall reaction time to just 10 minutes, and a high conversion of 98.1% was observed with full selectivity to solketal, and the activation of the catalyst after 6 run was due to surface poisoning and poor clocking of active sites by presence of glycerol in the catalyst matrix. These are the future trends of our product solketal, where we can see that increase in solketal synthesis can be seen in Middle East and European countries, and our product solketal can be seen, can be used in various type of food preservatives and surfactants as detergents, and also used in the synthesis of perfumes and perfumes. Thank you. That's all from my side. Thanks so much.